Welcome to this short presentation of the optical fleximeter MisuraFlex. The optical fleximeter was first developed by Expert System Solutions at the beginning of the year 2003, and it is one-of-a-kind instrument. The center of the sample bar is focused by a high magnification optic. The sample is 85 mm long and it is supported by two holding rods spaced 70 mm. A digital camera records all the shifts of the center of the bar, upward and downward. This instrument was conceived to study deflection phenomena which may be induced by temperature or humidity on material with no application of any external load. One of the typical applications is the determination of the coupling temperature between the body and the glaze, or between a laminated steel and an enamel, which is determined measuring the flexion of a glazed specimen according to the laboratory procedure known as Steger tensiometry. All the optical setup is completely protected and enclosed inside of a frame which can be precisely positioned using a micrometric screw. Managing in this way, it is possible to focus the sample very precisely. The resolution of the optical system is pushed up to the limit of 0.5 micron per pixel, thanks to the use of a blue light with a short wavelength. The measuring field is up to 3 mm upward and downward from the initial position of the sample. This is possible thanks to a computer-controlled linear translation stage which moves the optic to keep always the center of the sample inside of the field of view. The sample is a small bar long enough to be held by the sample holding rods, which are spaced 70 mm. If the test is carried out on a green sample, which is going to shrink during the firing, it is necessary to take in account the contraction in order to avoid that the sample may fall from the sample holders. The sample needed for the coupling temperature is simply a bar of glazed material which can be cut directly from a specimen of fire material. It is not necessary to prepare a specific specimen made on purpose for the test, like in the old Steger tensiometer. When the instrument is used to measure deflection due to the absorption of water, the keel can be left open and the water is applied directly on the sample. The beam of blue light which lights the center of the specimen has a wavelength of 478 nanometers and enables to reach the optical resolution of 0.5 micron per pixel of the digital camera. This is a recording of the measuring window during a test of coupling temperature between the glazed and the ceramic body. The camera is viewing the bottom side of the sample in order to have a fixed position at the beginning of the test, independent from the thickness of the specimen. The image of the center of the sample is moving downward or upward, and it is directly recorded in microns. We can clearly see here that the sample is bending downward up to 600 degrees centigrade, and then it starts to bend upward. If the image of the sample approaches the end of the measuring window, the linear stage controlled by the computer moves the optic and brings the image back into the field of view. This graph is the result of the measurement of deflection caused by the temperature increase on a sample of glazed ceramic body, which was cut from a wall tile. The sample is positioned with the glaze on the top side, and it undergoes a negative flexion because the body has a greater thermal expansion coefficient than the glaze. The deformation reaches the maximum in correspondence to the quartz transition, when the body reaches the maximum average thermal expansion coefficient. After this point, the flexion starts to decrease, and it reduces down to almost zero, because the reduction of the viscosity of the glassy phase allows the viscous flow and the absorption of the tension. When the temperature goes down, the glaze becomes rigid again and starts to build up tension, causing again deflection of the sample. This is the same result plotted as a function of temperature. We can clearly see that deflection reaches the maximum at the same temperature, both in heating and in cooling. This is the overlapping of the deflection curve with the thermal expansion of the body, which was previously measured with the optical dilatometer Misura LT. The blue curve is the thermal expansion of the body. The red curve is the average thermal expansion coefficient, while the green curve is the downward displacement of the center of the sample during the deflection test on the glazed sample, and the orange curve is the curvature of the sample bar, or the inverse of the curvature radius. We can clearly see that the maximum of deflection, or the maximum of the curvature, is in correspondence with the maximum of the thermal expansion coefficient. This graph plots the results of the tests obtained with the same heat treatment but with two different instruments. The red curve is the heat treatment, which was made of three segments: one ramp with constant heating rate up to 1200 degrees, followed by a period of time at constant temperature, and then the cooling. The blue curve is the sintering of the body, measured with the vertical optical dilatometer Misura HT, while the green curve is the deflection curve, measured with the fleximeter Misura Flex, on a sample of pressed raw body glazed with a layer of engobe. We can clearly see that at the beginning of the sintering, the glazed bar had a sharp flexion upward due to the fact that the engobe was shielding the body, delaying the sintering of the upper side. As a result, the bar bent upward. During the permanence at the top firing temperature, the bar recovered only part of the bending. This is also a graph which plots the results obtained with two different instruments. As in the previous case, the red curve is the heat treatment, which was the same for the two tests. In this case, the heat treatment was a continuous ramp up to 1170 degrees, followed by a stairway ramp with holding temperature at 1170, 1190, 1200, 1210 and 1220. The green curve is the sintering curve, measured with the vertical optical dilatometer Misura HT, while the blue curve is deflection, measured with the optical fleximeter Misura Flex. This is for sure an unexpected behavior, because it shows that the material is deforming much more under its own weight at 1170 degrees, compared with the deformation which happens at 1220 degrees. The reason for this weird behavior is due to the fact that this body contains too much fluxes, which start to develop a low melting glassy phase at relatively low temperatures. These glassy phases promote the sintering, but reduce the pyroplasticity too much. At higher temperatures, the glassy phases becomes more viscous thanks to the reaction with silica and alumina from the clay matrix, and the body becomes more and more stiff. The optical fleximeter can be used also for the measurement of the deformation which are not induced by temperature. The results shown on this graph were recorded during a test of deformation of a green ceramic body due to the absorption of water at room temperature. This test was carried out on a small bar of raw body pressed at different specific pressures. The bars were wetted with the same quantity of water on the upper surface. The material undergoes an initial deformation followed by a complete recovery within 10 minutes. This graph is the result of a second series of tests carried out on the same material but with a different wetting procedure. The same amount of water was applied but in 4 steps, delayed 3 minutes from each other. The result is impressive. Wetting the body in subsequent steps, the amount of deformation is much greater than wetting all at once. Besides the amount of deformation, here there is almost no recovery.